All right. So up till this point, we've been dealing with functions individually. Now we're going to actually start putting functions together. Function operations: addition, multiplication, subtraction, division. And they give you the notation here for them, which is the notation that hopefully you have seen before, plus a little dot, multiplication, minus, and then the line for division. You have given, in this particular case, you've been given two different functions and they want you to add them. You add your functions. They want you to multiply them. You multiply your functions. Subtraction, division. Now, division does have a little caveat here, meaning your denominator cannot be equal to 0. So once you do division, your domain can potentially change. So typically for addition and subtraction and multiplication, your domain does not change. But for division, your domain could change because the function you're dividing by now has a limitation. It can't be 0 because you can't have a 0 in the denominator. But other than that, it's just basic what you've always known with like terms and such. So let's look at the first example here. Let f of x be 3x plus 8. Let g of x be 2x minus 12. Find f plus g and find f minus g and their domains. All right? And their domains. So let's look at f plus g. F plus g, right, of x. Well, you are literally going to say 3x plus 8 plus 2x minus 12. When I am adding functions, I just add my like terms. What are my like terms here? 3x and 2x. So that's going to be 5x. 8 and negative 12. So that means f plus g equals 5x minus 4. That's it. Domain. Are there any strict restrictions on that? Are there restrictions? Is there any x you cannot put in there? No. So we're going to say all real numbers. What about range? No. All real numbers. All right. Let's look at the next one. Told y'all would like this. All right. F minus g. I will say pay attention to subtraction here because this is where I get the most common mistakes. 3x plus 8 minus 2x minus 12. Now, when I added, the parentheses were unnecessary. When I subtract, the parentheses are necessary. Because the most common mistake here is people just subtract that 2x and they ignore that negative 12. All right? So we are subtracting. We're going to subtract our like terms. 3x minus 2x gives me what? X. 8 minus a negative 12.
20.
Yeah, plus a positive. So we're going to say x plus 20 here. So that means f minus g of x equals x plus 20. All right, x plus 20. Again, in this particular case, there are no restrictions on domain. There are no restrictions on range. All right, multiplying and dividing. So pay attention to the notation because we're about to do one that looks similar. Multiplication, the little dot. Division, of course, is what you've always known since your high school world of division. Multiplication. So if I'm doing multiplication of my functions, I'm going to say x squared minus 1 times x plus 1. I need to FOIL. X squared times x. X squared times 1. Negative 1 times x, negative 1 times 1. All right? So foiling, that's all you're doing when you multiply functions here. You're just foiling. All right? Look at division. For division, make sure you put numerator what they asked, denominator what they asked. They want f over g. So we're going to put our f, x squared minus 1, divided by our g, x plus 1. You do want to look for some simplifying here. I can actually factor that x squared minus 1. How can I factor it? All right, so if I have a squared minus b squared, that equals a plus b. For the first one, subtract square root of the second one. So this would factor to x plus 1, x minus 1. All right? All over x plus 1. What can I simplify here? The x plus 1. So this is going to be x minus 1 as my answer. However, the domain for this guy did not change, right? I can do any x's and any y's. The domain for this one, are there limitations on it? Yeah. You have to limit before you simplify. So my limitation here for my domain is x cannot equal -1. That's the only limitation that I have for my domain.
How do you know?
Because -1 would make that denominator 0. I'm looking for what makes that 0. That's a limitation. So multiplication, you should have distributed your 2x and your -1 through and then combined any like terms. You would have gotten 12x cubed plus 8x minus 17x plus 5. All real numbers is your domain there. For f of g, we'll make it bigger so you can see it. It would simplify to 3x plus 5, but before you simplified it, your denominator had an exception of 1/2. Domain cannot be 1/2. Let's do f over g. So we have 6x squared plus 7x minus 5 over g of 2x minus 1. By the way, this is where we get our domain exception of 1/2. 1/2 will make that 0. We're going to factor our numerator. We have 6 times -5 is -30. Factors of -30 that add up to 7. So positive 10 and -3, right? So positive 10 and -3. So we have 6x squared plus 10x minus 3x minus 5 over our 2x minus 1. We factor by grouping. When we group behind a negative, we change it. This will have a 2x that comes out. We'll get 3x plus 5. This doesn't have anything that comes out, so we'll get 3x plus 5. So we end up with 2x minus 1 times 3x plus 5 all over 2x minus 1. My 2x minus 1's cancel, and I'm left with 3x plus 5. All right, let's talk about composite function. The diagram below shows what happens when you apply one function after another. All right, so you have an input, and you put it into the first function here, right? First input into the first function being x squared. So if I put an x in, I'm going to get x squared. My output is x squared. All right. Then I have this second function. I'm going to take this answer, my x squared, and I'm going to put it into my next function. So I'm going to plug it in for x. So I'm going to put the x squared in and plug it in for x. And my second output would be x squared. So if I start with x and the x process goes through two functions here that look like this, my final output will be x squared plus 4, and that is what composite is. It's when you take two different functions and you compile them back to back. All right, so with composite, you have to know your notation. Make sure you know notation, G of F does not mean multiplication. That means composite. And you always put the one that is closest to the variable inside the other one. All right, let's example. Let f of x equal x minus 2 and g of x equal x squared. Find g of f of negative 5. G of f of negative 5. So when we do this, we are going to take the negative 5 and we are going to plug it into the f first. And then we are going to take that answer, whatever we get there, and we're going to plug that answer into g. Okay? So we're going to say f of negative 5, and we're going to take that answer and we're going to plug that answer into g. So first, f of negative 5. F of negative 5, that just means evaluate, so plug it in here. Negative 5 minus 2 equals what? Negative 7. I'm going to take that answer and I'm going to put it into my g function, all right, into my g. So my g is up here. So g then of negative 7 would be negative 7 squared, or positive 49. So that means g of f of negative 5 equals 49. Another way they would write it, g of f of negative 5 equals 49. So the second question here is a composite of functions commutative? What does commutative mean? Yeah, 2 plus 3 equals 3 plus 2, right? Addition is commutative, subtraction is not. Multiplication is, division is not. Composite is not. Because for our example, we did g of f and we got 49. For this check understanding, we did f of g and we got 23. So it is not commutative. You cannot go different directions and get the same answer. You cannot do that, okay? Question. Another method for solving this. Another method for solving this is to do the composite first and then plug in the 5, or the negative 5, all right? So I have f of g, and I'm just going to do of x with no variable, which means I'm going to take the entire g function and plug it into f. So f is x minus 2, and g is x squared. So if I do this composite first, I'm going to take the x squared, the g, and I'm going to put it into the f. So my f of g function will look like this. X squared minus 2. That's my function. All right, and that's going to work for any number that I plug in to evaluate. And then I can evaluate that function at negative 5. So f then of g of negative 5 would be negative 5 squared minus 2, which is 23. Two different ways. If you have the number, you can plug it in, plug the answer in. All right? Or you can do the composite first and get a new function and plug in the number. There are going to be times when it asks you to do the composite without plugging in a number. They want the new function, and that's what the new function would be, x squared minus 2. All right, let's look at the next example. They have this word problem. So page 394. Suppose you're shopping in the store in the photo. You have a coupon worth $5 off any item. You'll notice in the photo that we have 20% off. So it says use functions to model discounting an item by 20% and to model applying the coupon. All right, so we're going to have two different functions here. Our first function is going to be if we just apply the coupon. It's going to be our original price minus 20% of our original price, right? So what is 1x minus 0.2x? 1 minus 0.2 is 0.8x. That is my coupon. That's what I would pay for my item if I applied the discount, right? My second function, g of x. I have a $5 coupon. Let's just say I buy something with my $5 coupon. What does that function look like? Well, it's whatever it cost minus 5. That's that function there, right? So my function with the coupon would be 0.8x. That's what I would pay for that item. My function with just the $5 off would be x minus 5. Those are my two different functions. Now it says, use a composition of your two functions to model how much you would pay for an item if the clerk applies the discount first and then the coupon. The discount, the 20% first, and then the coupon, okay? So if I'm gonna apply the percent off first and then do the $5 coupon, the $5 coupon has to be furthest away, all right? So that means I want to do G of F. Because remember, you work inside out. This would be applying the discount and then applying the coupon. G of F. So I'm going to take my F function and I'm going to plug it into G. All right? So this would look like this, 0.8x minus the $5. That would be that composite, right? That would be that composite. Next question. Use a composition of functions if they applied the coupon first and then the discount. All right? So if I apply the coupon first, then I am going to have that one closest to my x, and I'm going to say f of g. Now I'm going to take my g function and I'm going to plug it into my f, right? So this is going to say 0.8, and instead of x, I'm going to write x minus 5. X minus 5. So we're going to go ahead and distribute that. 0.8x minus, what's 0.8 of 5? Point is 4, right? 0.8 of 5 is 4. So this is the composite if I do the discount and then my $5 coupon. This is the composite if I do the coupon first and then the discount, all right? So it's just a composite one way or the other. Now, the last question. How much more money is any item if they apply the coupon first? The coupon first, yeah. So I'm just going to subtract them. I'm going to take my 0.8x minus 4 minus, this is a addition or subtraction, right, of two functions, 0.8x minus 5. Combine my like terms. 0.8x minus 0.8x, those cancel. Negative 4 minus a negative 5 is 1. So if they apply the coupon first, I'm paying $1 more for any item. It doesn't matter how much the item costs. I'm paying $1 first because nowhere in here did I actually put in what I paid for the item.